if you've ever worked with redstone before, you've probably been in a situation where you had to cross some wires kind of like this, and you probably used a similar solution, didn't really think much of it. After all, I mean, it would make sense that if wires have to cross, I mean, obviously, geometrically, there's no way you could get around that, right? I mean, at the very least, you could make the crossing a bit more compact, or you could use certain redstone specific mechanics to get the signal to just cross right through itself. For example, you could use skulk sensors, like so, though this only really gives you pulses, but you could also use comparator read-through, kind of like this. Here we're modifying the droppers so that, it just moves back and forth based on if the redstone is on, and then the comparators read through the exact same block. But we're not here for any of that today. No, we're here for this weird solution. At first glance, this doesn't look at all like it should be able to cross wires. It's just a bunch of random comparators, right? Well, actually, no. It has no problems crossing wires. In fact, it does it so well that it even is able to preserve the signal strength at the same time. Now, this isn't even some sort of weird comparator-specific mechanic. No, we're just using basic logic here. And so the question is, how do we cross wires without even crossing any wires? Well, let's actually start by looking back at this method over here. This utilizes the fact that we're not transporting physical entities, but rather, information. So first we convert the information into a form that passes through itself freely, and then convert it back. But as for what we're going through here, even if we convert it into a different form of information, it still can't just cross over itself without one of these special mechanics. So we're going to have to think a little bit outside the box. Well, first off, in computing, there's more than one way to get information somewhere. The most obvious way and direct way is to just simply replace any information that's already there. However, we could also modify whatever's there into the number we want. One of the biggest examples of this can be found in low-level computer programming. If we took a program containing this innocent little line of code, we'd get an instruction that sets the number to 5. Pretty straightforward. If you want to set something to a specific number, use the instruction that sets things to specific numbers. And we would get this exact same result, no matter what number we want to set it to, even if it's another variable. Well, unless we specifically said to set the number to 0. Instead of getting what you would expect, we get a subtract instruction? Well, actually, that is because taking into account all the optimizations in modern processors, it's simply less work to subtract something from itself than to load in an arbitrary value. So what if we try to apply a similar concept to the problem we're trying to solve here? Well, this means the challenge here is no longer to physically get both values to the opposite side, but to instead individually change both values into each other. Let's start with binary. Binary is pretty easy. There's only 4 possibilities. And we can make things even easier by splitting it into 2 types. The cases where they're the same, and the cases where they're different. If the 2 bits are identical, swapping them is pretty easy because we don't actually have to do anything. Ones are ones and zeros are zeros, so nobody's going to notice if we don't actually swap the values. So we can just map them straight through and consider them swapped. However, that only works when the 2 bits are already the same. If the 2 bits are different, we get the wrong answers. But wait a second, in binary there's only 2 possible answers, so if we know that all the bits are always wrong, we could just invert them, and now all of the bits are always right. Well, at least if the 2 bits were different, that is. So now we have 2 relatively simple circuits, and every case is covered by one of them. It may not seem like the most elegant way, but I mean, remember, bits are bits. Nobody's going to tell the difference as long as we get the correct numbers to the correct spots. So now all that's left to do is combine them into a single circuit that can do both methods. If you want to take a moment and pause the video to see if you can figure it out yourself, now would be a good time to do so. And I do recommend it if you're up for the challenge. Whenever you have to sometimes invert and sometimes not invert, an XOR gate is a great place to start. If you supply a 0 on one side, the XOR gate acts entirely like a buffer. And with a 1, it acts like an inverter. And so swapping out everything with XOR gates is pretty easy to alternate between the two possibilities. By putting a 0 in the middle, it is able to swap identical bits, and by putting a 1 in the middle, it's able to swap opposite bits. Though this isn't quite enough, we still have to manually choose between the two possibilities. So, well, okay, maybe it's once we try to switch automatically, that's when we suddenly have to cross wires again, right? Well, all we need here is a circuit that outputs a 0 if the two numbers are the same, or a 1 if they're different. But that just so happens to also be an XOR gate. And before we know it, we're already handling all 4 cases using the exact same circuit, which means it works in the general case. It can swap any 2 bits using just 3 XOR gates and 0 wires crossing. Of course, that all hinges on us being able to make an XOR gate without crossing wires, but the good news is that is more than possible. Here in the world download, let's actually test out the circuits. Here we have a version that just uses basic repeater and torch logic, proving that it works with even the most basic of logic, even if it can end up being a little bit complicated. But here we have one that uses comparators and is really sneaky about the signal strength in order to be quite fast, actually. But you may start to wonder, have we really accomplished anything here? Like, sure, crossing wires is often not the most efficient thing to do, but generally not so bad as to replace it with all of this. Well, for starters, I would argue that the answer to the question of whether we've accomplished something is just fundamentally always yes, even if something's really impractical or already discovered 1,000 times. But today is not the day for that soapbox. But even aside from that, as impractical as these kinds of circuits may be, their very existence definitively proves that crossing wires is never necessary for logical redstone, no matter how complex the goal is. That said, it makes no claim as to how simple that alternative may be, but also just the fact that you could theoretically make an entire processor in just one layer of redstone is kind of mind-blowing. So that's binary out of the way. But now what about signal strength? Well, let's actually start by taking a slightly different look at what's going on here. What we've done in a way is we've taken the original problem of trying to get both sides to exchange information and turn it into a problem where both sides have to exchange information. Except now, the information is always going to be the same no matter what. Because it's the same as itself, it doesn't need to cross over itself. And this works out pretty well because swapping is inherently very symmetric. No matter what one side does, the other very specifically does the exact opposite. So what if we try doing this sort of equal but opposite change using the most straightforward form of arithmetic, addition and subtraction? We'll start by computing the difference of the two numbers. I mean, that is, of course, the amount that both sides need to change by, though it might not be the correct sign, but that's not a problem. We can just add it on one side and subtract it on the other, and oh, what do you know? It works. And running through it on paper, we see that we do in fact get that sort of result. However, implementing this in Redstone isn't going to be that straightforward, as we can't really have negative numbers, and this difference is going to be negative half of the time. But there's a few ways around this. The first is that we don't necessarily have to use the full range of signal strengths. It's pretty easy to associate signal strength with hexadecimal, as there are in fact 16 values, but we could also use octal. Now, octal doesn't sound that great at first because it's only half the size, but as it turns out, that's actually only a single less bit, but it has the advantage of now we have half of the range to make intermediate calculations a lot simpler. In this case, it's the perfect amount of range. We could just make 7 mean a difference of 0. Anything less than that is a negative difference, and anything higher is a positive difference. We don't even need all 16 values. Alternatively, we could use two separate wires, one representing a negative difference, and the other representing a positive difference. Though this kind of poses a problem. I mean, now we're right back to having two wires again. So we're just going to have to cross wires again, right? Well, actually, the funny thing is, if we just route it right back through the exact same difference circuit again, it actually just swaps the two outputs. Now you may be thinking, well, if we could do that, why didn't we just do that on the first part? Well, that's because, well, this thing can theoretically swap two values. It can only do it if one of the numbers is already 0. The final way around negative numbers, and my personal favorite, is to start with addition instead, and then subtract off each side, which basically means that each side is left with whatever part of the sum it doesn't contribute, which is always the other side. However, this doesn't really do a whole lot, as it's only really viable for octal. If we tried to do it with hex, we'd have to start doing modular arithmetic, and it's just slower than using two wires to represent the difference. And here we have both of the circuits in redstone form. The octal version actually does start with addition. It turns out to be ever so slightly faster, but of course, hex does the whole double difference stuff, and yeah. And this also does a pretty good job of demonstrating how even though an octal signal contains 25% less information than a hex signal, it more than makes up for it in just how much simpler the redstone tends to be. But what if we went the other way? What if we put a lot of information into a single signal? There's one final branch of redstone that we're looking at today, and unlike the others that we've looked at so far, here, this circuitry is legitimately irreplaceable. As it turns out, comparators on Java Edition don't actually limit their own output to 15, at least at the time of making this video. This means if you put a lot more items into a container than are supposed to fit, it will make an accordingly strong output. If we were to use /dataget on this comparator, as I was saying, we get that it is outputting 897, which is definitely a little higher than it's supposed to be. However, where this becomes really useful is that you can actually pass this signal around through other comparators, even through the sides and through solid blocks. As you can see, normally this should not be possible. Normally, if you have 15 in the back, you should not be able to cut it off with compare mode. And yet, because this is outputting higher than 15, it works. Technically, you don't actually have to use a barrel. You could, for example, use a chiseled bookshelf, in which case you can go all the way up to the signed 32-bit integer limit. I'd say it's probably not too surprising that this is a slightly controversial thing to do, but I personally enjoy it. However, HSS has one big catch to it. While you're free to use comparators and solid blocks all you want, Redstone Dust actually does limit its level to 15. But if you can't use Redstone Dust, how are you supposed to move the signal vertically? Well, you see, that's just the thing. You don't. Which means the only way for HSS to cross over itself is using arithmetic. I've included a couple examples in the world download. There's actually two versions of the world download. One of them does not contain the HSS. And that is because, right as I was working on this video, Mojang went ahead and made it so that overstacked items no longer work. And by no longer work, I mean the game will stop working. It just simply crashes if you load a chunk with overstacked items in it. So, back to the useless realm, I guess. Anyways, on that note, world downloads for both Java and Bedrock are in the description, and here's some diagrams on the screen to help things out. If you enjoyed the video, be sure to do all the algorithm boosting things. YouTube Analytics tells me that 104% of my viewers have never committed voter fraud, and with that, I will see you next time. Trans rights, by the way.